We see some trends in the individual groups. In the alkali metals, what we see going down, we've already talked about atomic radius. Atomic radius increases as we go down. The density increases as we go down, and reactivity increases. So things like cesium are more reactive than sodium. Sodium is more reactive than lithium. And just having a general understanding of these trends can be a useful thing. Going down the column, we see that ionization energy decreases, electron affinity decreases, and the melting point also decreases. These guys in general have very low ionization energies. That makes them good reducing agents. They're very easy to oxidize. They're very reactive. We don't find them as elements in nature because they combine with just about anything that's around. And the compounds that they make are generally quite soluble in water. Some of the reactions that these guys undergo, they will react vigorously with nonmetals such as the halogens. So here's M for the alkali metal. The metal will react with a halogen, and then you'll form metal halide salts. They react explosively with water. And here we see the difference in the reactivity. So lithium will bubble and fizz in water. Sodium, what they're doing is they're releasing hydrogen gas, and the reaction is exothermic. It's releasing heat. And so for sodium, it releases enough heat to ignite the hydrogen. Potassium's even more reactive. And so they're generating hydrogen gas and heat, and it explodes. So it's no wonder that these aren't found in nature. Yes? Francium, I would predict, would be even more reactive. Francium is radioactive, and so it's kind of hard to deal with. In the halogens, as we go down the column, we see that the atomic radius increases, the density increases, the melting point increases. I think that's opposite. For the alkali metals, the melting point decreased going down. You know, if you needed to predict the trend for melting point in the halogens, you could do that by looking at the periodic table, because we see that the ones at the top are gases at room temperature, bromine's a liquid, and iodine's a solid. So as we go down, the melting point is increasing. We see that the ionization energy decreases, and again, we see that the reactivity increases. These guys have very high electron affinities. So, they're just on the opposite side of the noble gases from the alkali metals. So they're good oxidizing agents. They're very easy to reduce. The alkali metals were good reducing agents. Also very reactive, and their compounds are generally soluble in water. They react with metals to form metal halides. And they also react with hydrogen to form hydrogen halides. And they're very reactive, and so this is an exothermic process. So write a balanced chemical equation for each reaction. This is the kind of stuff that I always found really tough as a student. Like, what? So let's look at aluminum, metal, and chlorine gas. Well, let's start off with aluminum and chlorine gas. What do we know about chlorine? Is it a diatomic element? Yeah, it is. So its formula is going to be Cl2. Well, metals and halogens form ionic compounds. So do we know what charges aluminum and chlorine will like to have? Yeah, so we know that aluminum makes a +3 ion and chlorine makes a -1 ion. So we can predict that the formula is going to be AlCl3. an ionic compound, is that going to be a gas, a liquid, or a solid? What do you think? It's going to be a solid, most likely. Most ionic compounds are solids at room temperature. So I'm going to put a solid in there. And then we just have to balance it. So I've got 3 chlorines. If I put a 2 here, then I could get 6. And I could put 3 there and get 6. I need a 2 over here. Any questions? How about reaction between lithium metal and liquid water? Well, lithium is going to be a solid, and the water's liquid. Those alkali metals release hydrogen. That's what makes them explode. So somehow we're going to get H2 gas. And then what do we have left here? If the H2 goes into hydrogen, then we've got lithium and we've got oxygen or perhaps hydroxide. Let's go back and look at this. So this is telling us that the metal reacts with water and it forms a metal hydroxide, which would be aqueous, and the hydrogen gas. And that, that's one of those things you just kind of have to learn how to remember. So that would be lithium hydroxide. Because this is happening in water, that would be aqueous. And then everything's good here except for those hydrogens, right? I'm going to have to put a 2 here and get a 2 over there. A 2 over there, is that good? Any questions? How about gaseous hydrogen and liquid bromine? Well, both of these are diatomic elements, right? The halogens react with hydrogen to form hydrogen halides. Well, these are not ionic compounds, but these are acids. If we put them in water, they become ionic, and so we can predict their formulas by looking at those charges. So this would be HBr. Those are generally going to be gases. I wouldn't really expect you to know that, though. Questions? Yes.
Okay, so HBr, when it's a liquid, they call it hydrobromic acid, but when it's a gas, would it just be hydrogen bromide?
When it's a gas, a pure compound, it's called hydrogen bromide. It's an acid when it's dissolved in water. So if it said AQ, then we'd call it hydrobromic acid. Any other questions? Noble gases have some trends as well. Atomic radius increases as we go down. Boiling point also increases, density increases. Their ionization energies are just really, really high. So even though it decreases a little bit as you go down, it's still crazy high. They are only found uncombined in nature. We use them to create an inert atmosphere for things that are very reactive. Before the 1960s, there were no compounds of noble gases that were known. Now we know about a few of them. Because, people take that as a personal challenge. Oh, so you tell me there aren't any compounds with noble gases? I'm going to make it my life's work to make one, right? It's just kind of a science attitude, yeah.
So does that mean if there's possibly more noble gases? Or?
I don't think there are more noble gases. It's that element 118, I don't know what he's like. Are there more possible compounds that include noble gases? That's possible, but we just haven't figured out how to make them. They're not probably going to be very stable, but yeah. No wild cheering? And that's the end of the chapter.
That's right.
Oh.